Okay, so in our previous videos, we've talked about integrals, derivatives, limits, all kinds of stuff to get you through calculus. But now we want to turn to applications of calculus. So in addition to this video, we also have application to economics. But here, I want to show you an application to physics. So what I have written on the board is called Faraday's Law. This object right here, named after Michael Faraday, one of the greatest experimentalists to ever live. Now what this law talks about is what's called electromagnetic induction. So instead of teaching you how to maybe calculate a new integral or take new derivatives, what I want to do is teach you how calculus can be used to interpret things. So let's talk about this. So this V right here, this stands for voltage. So you may have heard of voltage when you screw in a light bulb, when you talk about powering your laptop or batteries. Voltage is basically, it talks about circuits. It talks about how currents can flow in a circuit and how much energy it takes for that current to flow, more or less. Now this B, for some reason, we call a magnetic field. Okay, so we just give it the symbol B. A is area and T is time, and I've written these over here so I can keep them the whole time. So what does this say? Well, first off, you need to know that whenever you have a voltage in a circuit, current will flow. Just like when you hook up a battery, a 9-volt battery to a circuit, to your remote or a small car, a current will start to flow and you can use energy from the battery. So whenever this is non-zero, you're going to have a current in the circuit. So that's important to remember. So when V is non-zero, you get a current. And a current is nothing but the flow of electricity. Okay, so when is this not zero? Well, when this side is not zero. But what is that side? So what we're doing is we're taking the integral of a magnetic field over an area. But you have to remember that an integral is a sum, right? An integral is nothing more than a summation. It's a Riemann sum. So what we're doing is saying we're adding up how much electric field there is in a given area. So if we have a cylinder, if we want to add up how much electric field is in that cylinder, we just do an integral. We add up all the electric fields over some area right here. That's all we do. Okay, so this is just adding up electric or magnetic fields. But we're taking the time derivative of that. So what does that mean? That's saying we're looking at how the magnetic field is changing in that area. So if we have a cylinder and our magnetic field is not changing, it's just a static magnetic field, then the rate of change is zero. It will have no voltage, no current running. However, if we have this same cylinder, and for instance, instead of having just a constant magnet flowing throughout it, let's say that we have a little magnet. So this has its own magnetic field. And let's say we drop that through here. Well, at first, there's no magnetic field in here because it's above the copper. However, when it starts to fall and we get a magnet here, there will be a magnetic field in this region. And as it keeps falling, the places that had no magnetic field to begin with will start to experience a magnetic field. Therefore, the rate of change of summing up our magnetic fields will not be zero. So, what this tells me is that in order for V to be non-zero, then we need a changing magnet. We could also have a changing area, but we'll assume the area is constant here, just a cylinder. So we need a magnetic field to be changing as it falls in order for there to be a current or voltage. But what about this negative sign? Could it mean anything? It's just a small negative sign. The negative sign makes all the difference in the world. So the negative sign says whatever voltage is created from this field will oppose this side of the equation. So whatever voltage you set up will oppose the magnetic field, the changing field. So what will happen is, as this falls, a voltage will be set up, which means a current will run. So a current's going to start running. And what it's going to do is oppose the magnet. So it's actually going to slow down the magnet because of this negative sign. And so every little piece of this equation tells you something physically different. And that's the really cool part of calculus. This part tells you we're summing up the fields. This part tells you we're looking at the rate of change of the fields instead of just the field by itself. And this part says we're going to oppose whatever this is. So there's lots of physical intuition that goes into calculus. Now, instead of me just saying all this and, you taking my word that it works, we're actually going to look at this. We're going to drop a small magnet through a conducting pipe and show you that it will indeed oppose this magnet. We're also going to show you that if you have, instead of a copper pipe, you have a superconductor that has no resistance, it'll oppose it perfectly, and it will not fall. The magnet will levitate because of this negative sign. Okay, so let's do that. Now, it's also important to note that this is not scraping against the side. This is falling freely through it, but the magnetic field is changing. So ddt of the magnetic field is non-zero, and it just now hit the ground. So that shows that there was an induced current because the derivative was non-zero. And since there's a negative sign in Faraday's law, it opposes the magnetic field. Thus, the magnet slows down. A lot. A lot. Okay, so here we have what's called a superconductor. And a superconductor is an object such that when it's in its superconducting state, a current can flow through it without any kind of resistance. So in order to get it to its superconducting state, we have to make it extremely cold. And to do that, we use liquid nitrogen. So be very careful, and of course always use gloves and eye protection, and always do this in a very large ventilated room. Okay, so once that cools down, we are going to put this very, very strong magnet in it. So what this magnet is going to do is it's going to induce a current, but unlike the copper, when I induce this current, that current won't stop. So this will be held up very well, and we'll see just how well as soon as this stops boiling. When it stops boiling, they're at the same temperature. Give you a little more nitrogen. Okay, so that's pretty cold, so let's give it a try. What do you know? The magnet floats. And not only does it float, you can spin it. And it'll keep doing that. It would keep doing that forever if there was no air in the room to cool it down. However, because there's air, it'll eventually stop and cool down. But, as you can see, there's nothing holding it up except for magnetic forces. And this is really the best way to see Faraday's law.